This is my final chump build. Each of my ICs are marked with some Sharpie and electrical tape. I've got program EEPROM, control EEPROM, NAND gate, program counter, accumulator, ALU, multiplexer, NOT, inverter, RAM, address register, and this is my Ben Eater clock build. These LEDs are the program counter outputs. These are the multiplexer outputs, the accumulator outputs. This is the accumulator enable pin, the ALU function select pins, the RAM inputs, RAM address selection, RAM read-write bit, and these are the RAM outputs through the inverter. To begin, these black wires here from the upper nibble of program EEPROM to the address pins of control EEPROM are for the opcode. These dictate what control codes will be sent out across the entirety of the chump. These opcodes are the I/O pins from the control EEPROM. So these black wires here feed into the ALU, accumulator, and address register. 6 of them go into the ALU through the function select pins, carry in and mode select pin, the accumulator enable pin, and the address register for the read-write bit of RAM, following this data path here. Next, these yellow wires dictate the inputs to the multiplexer. So the constant portion of the code comes from the lower nibble of program EEPROM. This is fed into the A inputs of the multiplexer. The B inputs of the multiplexer are the inverted RAM outputs, because the RAM outputs are already inverted, so we'll invert them back. The multiplexer's select pin comes from IO4 of the program EEPROM to select between constant or memory command. The multiplexer outputs through these gray and blue wires. The blue wires go to the ALU-B input pins. The gray wires go here to input into the A through D of the program counter, as well as into the address register in Q1 through Q4. Next, these blue wires here come from the output of the accumulator into the ALU A pins, A input pins, as well as the RAM input pins through these gray wires. The RAM address pins are connected by these gray wires here coming from the output of the address register. Important connections to note are 10K pull-up resistors on all the RAM outputs, because the RAM outputs are open collector, so you need to add 1K or more pull-up resistors. I chose 10K. As well as the ALU A equals B pin is a 2.2K ohm pull-up resistor. Up on the NAND gate is my function, my go-to and F0 combinational logic circuit. So the IO7 and IO6 run through a NAND gate. The output of this NAND gate is then fed into another NAND gate, which have its inputs tied together. This functions to create an AND gate out of a NAND gate. This output is fed into another NAND gate with the ALU A equals B pin, and finally fed into the load pin of the program counter. Other than that, just make sure that the chip select, write enable, and output enable pins on all the ICs are connected correctly. So let's run through my code flashed onto my program EEPROM. So we're going to go to a load 0 command. And we're going to store that to 2. So on the next clock cycle in address 2, we'll be putting a 0. As well, load 5. We'll put a 5 into the accumulator. I'm going to store that to address 1. So in address 1, there should be a 5 now. As well, in this line is a read 2 command, so we read that too. We're going to load what's in address 2. It's currently a 0. We're going to read what's in address 1. And we're going to add them. So 0 plus a 5 should equal a 5, shown here. This is least significant to most significant bit. least significant to most significant, least significant to most significant. The opposite of the normal way you'd look at it. After the adder, we're going to store that into address 2 again. So now we're going to read a 1. So we're going to read what's in address 1. It's a 5. We're going to load it. We're going to subtract 1. It's now a 4. We're going to check if it's 0. If it's not 0, we're going to keep going. And the next command is a go to 3 command. So we're going to go to line 3, shown by the program counter outputs. So in 3, we're going to store that 4 into address 1. There's a 1, and that's my 4, least significant to most significant. Next, we're going to read a 2. Load it. We're loading what's in address 2. We're going to read what's in 1. We're going to add them. So 5 plus a 4 should be a 9. That's an 8 and a 1, so we have a 9. We're going to store that to address 2, so we're going to put a 9 into address 2. Now we're going to read what's in address 1 and load it, which is a 4. We're going to subtract 1 from it again. It's a 3. And now we're going to check if it's 0. It's still not, so we're going to keep going. Go to 3. We're back at line 3. We're going to store that 3 into address 1. Then we're going to read what's in address 2. We're going to load it. And then we're going to read what's in 1. We're going to add it. So a 9 plus a 3 should be a 12, which is what's shown here, 8 and a 4. Continuing, we're going to store that into address 2. So our 12 is being stored into address 2. And we're going to read a 1. And we're going to load it. We're going to load the 3 that was in address 1. We're going to subtract 1. It's now a 2. We're going to check if it's 0. It's still not 0, so we're going to have a go to 3 command. Going to line 3. We're going to store that 3 back in we're going to store that 2, back in address 1. We're going to read what's in address 2. Load it. It's a 12. We're going to add a 2. We're going to read what's in 1, We're going to add it, which was a 2. So now we have 14. We're going to store that back into address 2. The 14 is being stored in address 2. We're going to read what's in 1 and load it. It's a 2. We're going to subtract 1, so it should be a 1. It's a 1. We're going to check if it's 0. It's still not 0. We're going to go to line 3 now. Store that 1 into address 1. Next, we're going to read a 2. Load it. So there's a 14 in address 2. We're going to read what's in 1. And we're going to add it. So 14 plus 1 should be 15. We have a 15. We're going to store that to address 2 again. 15 is being stored to address 2. We're going to read what's in address 1 and load it. It's a 1. We subtract 1. Check if it's 0. It's now a 0. So when it's 0, we should go to line 14. Line 14. And at line 14 is an infinite loop saying go to 14 at line 14. So no matter how many times I pulse the clock, my code will stay here. Yeah, so that's the completed code. Really, really proud of this thing. It's awesome.